and learning and collaboration, both at a kind of research level, but also at a teaching and kind of sharing of ideas level. And the idea is kind of to share knowledge for the benefit of everybody, and to kind of also have cultural interactions and exchanges, as well as on the academic level. So they have funding that's available to basically encourage new networks, and part of the idea is that, as well as working together on an idea of mathematical interest, we're going to encourage further collaboration between our respective groups and departments and universities. So how did we decide to do this project? Well, we three are based at 3 of these partner universities, and there was this funding call for this digitalized topic. And the kind of broad theme of this is how do digital technologies shape societies? And within this, there are kind of these 4 different sub areas. And so it kind of goes with the kind of philosophy of Uni Europa and kind of bringing people together, impact of research on the broader community, kind of within the universities, but also like the wider national community. And so here's a whole list of different things that digital technologies can do for us and are doing. And we're kind of interested in new algorithms to aid decision making. And so we're thinking of this in the context of machine learning type ideas, where we want to have algorithms that help us maybe classify or pick between different topics, but not just from a mathematical perspective, also thinking about the kind of broader aspects, including kind of impact of decision making and the wider context there. So a very brief overview on this project. So the funding is basically for about 6 months worth of time, maybe a little longer. And it is to generate new ideas that kind of are a bit high risk, but potentially high impact. So it's kind of to trial a new idea to see if it has any merit. Hopefully the answer is yes. And then use that as the kind of starting board for bigger and better things. So the idea that we had is really taking this idea of decision making in a digitalized way and thinking about deep learning. So probably many of you are familiar with deep learning, but it's basically a data-driven machine learning tool, and often for solving these decision type problems. So we can think of it that I have a large number of data and I want to maybe classify them in some way. So a simple example would be, I have kind of a binary choice where something is on or off, and I've given some data. I want to say, is that going to be in the on class or the off class? I'm sure we've all seen these examples with image classification, where we want to differentiate between pictures of cars and cats and trees. And these are all kind of examples of problems that can be solved with these kind of data-driven approaches, but there are still quite a few challenges. So the interpretation we're thinking of is that we have some data and we don't necessarily have understanding of some kind of properties of that data. We just have a large data set. We don't necessarily know anything else about it. We want to learn how we get from our data set to those classes. So we can kind of think of this as a model. If I give you a particular input, what class am I going to have at the end? In order to do that classification accurately, I need to learn how to get from my input space to my classification. So we can think of this learning phase as a regression problem. So the idea that really kind of sparked this project was a new viewpoint. So in the kind of traditional machine learning approach, thinking of like neural networks, we have some inputs, we have some outputs, we classify a set where we train, we prescribe some kind of architecture, and then we want to learn what architecture best gives us from our inputs to our classes at the end. And then once we have this network, we can then solve it for new inputs and class them. But the problem is here, is that this training phase is often really expensive, and it's quite difficult to speed it up in the kind of traditional framework. In practice, a lot of people think that it's not really a problem because the idea is you can train once and then use your learning algorithm. Once you've got your network, use it loads. And so that's kind of a big upfront cost, but it's hopefully going to be amortized by applying it lots of times. But that's actually not really good enough, I don't think. If everyone's using these deep learning problems for lots of different problems, then proportionally the cost does become important. Also, you may want to update your model if you have new data. And so if you then have to redo your training phase and that's really expensive, that's quite unattractive. And so we were thinking about, is there a way to improve this training phase so that it's more efficient? And kind of the new viewpoint that we're thinking of or hoping to think of comes from applied mathematics. And instead of thinking about this learning phase as we have some network and we want to learn some parameters and we kind of go through backwards, you can actually rethink of this same problem or a related problem as an optimal control problem constrained by differential equations. And so that's nice because there's a whole rich mathematical literature about optimal control problems that are constrained. And the idea is that hopefully we can port some of that technology from particularly numerical linear algebra and ODE, PDE, to use a kind of a different sort of algorithm for this training phase. So this kind of is quite new in deep learning. And the hope is that we can adapt this training phase in some way such that we're all kind of numerical linear algebra people, that we can use our expertise within a different framework to improve this training phase. And so by improvements, what do I mean? I mean, maybe faster, maybe more computationally efficient, and just alternative to what the current framework is. And so the idea is to kind of have a look and see if this kind of approach or philosophy has some benefit for this problem. And that's kind of the idea of what we're going to be doing over the next few months. So as part of the project, we have a week-long visit to each of the partner universities. This is the first of our visits, so we're in the very early days of our collaboration. And that's why we're kind of presenting more of a philosophy today rather than any new work. So if you're interested in keeping up to date with what we're doing, part of the Uni Europa kind of philosophy is this sharing of ideas and open research. And so we're quite committed to discussing not only what we actually do, but the research process itself and what it means to kind of early career people to come together and work on new ideas. So the best place to keep up to date on what we're doing is our website here. If you want to go to it, you can follow this fancy QR code. We've also got a Twitter account, which I'll endeavour to keep somewhat active. But in particular, each of our visits, we're going to be hosting one of these half-day workshops. And with the speakers are happy to have their talks recorded, we're going to be hosting them on our YouTube channel. So as I said, this is the first of 3 research visits. We have 2 more planned, one to Bologna in July and one to Leuven in September. And each of those, we will also be organising a similar half-day workshop. So watch this space for announcements on those, and all of the information about that will be on our website. So that's kind of the overview of the project. We're now going to talk a bit about each of our universities and departments. So I think I'll pass over to Davide.
Thank you, Jemima. So as Jemima told you, one of the main goals of Uni Europa is basically to promoting interactions between the university and the consortium. And so we thought that this comes also with knowing better our university. So I'm sorry that I didn't find the slides in English, only the Italian one. So you can read it, but like many people cannot. But here just to show you some numbers. So the University of Bologna is the oldest university in the world. We like to say that. It has been founded in 1088. So some people say it's the oldest in the Western world. I'm fine with that. Okay. And it's also one of the largest in Italy. So we have, like last year, we had a little more than 90,000 students, and 7,000 were international students. So it's one of the most international places in Italy. And we also have a lot of like outgoing and ingoing students. So from Bologna, almost 2,000 students last year went abroad with the Erasmus Plus project, and 1,300 came to Bologna. So if you have like students, for instance, or I mean, also you want to come to Bologna because you think it's a great experience, you have like all the tools to do it, and we'll be welcoming you for sure with a lot of like good food, for instance. And so we have like these huge numbers, but unfortunately, I would say the numerical analysis group in Bologna is not that large. We are only 13 people, and we have at the moment only 5 PhD students. And in particular, the main research topics that we focus on are these 3 here. So numerical linear algebra, of course, and optimization, and that's me. You probably know Valeria Simoncini and Margherita Porcelli that's gonna talk later. I would say like most of the people in Bologna work on inverse problems, especially dedicated to the to imaging, so image restoration, the blurring, this kind of things, but also geometric modeling and processing. So again, one of the goal of Una Europa is also to try to increase the interaction between our university. We have a lot of like common interests between the different research group in numerical analysis and scientific computing in Edinburgh, Leuven, and Bologna. But at this moment, I think all this like overlapping of research interests is not exploited so much. So we hope that this is going to be one of the first joint research projects that we see in the future about deep learning or other topics. Because we see a lot of potential. So it's basically what I wanted to tell you about Bologna. And we have this nice picture of Edinburgh again.
Yeah. So we didn't have any nice graphics I could find on the website, but Nick very helpfully took this beautiful photo on our first day of our visit. So the University of Edinburgh has quite a lot going on in general, but the School of Mathematics is quite large. So I think the most recent figures I looked at were there are over 200 academic staff, 800 undergraduates, 300 MSc students, and 180 PhD students as of September last year, I think. So the way it's divided, the kind of groups that have the most direct interest in this project, there are kind of 2 of them. So one is the Applied and Computational Maths group, which I'm in. So we have interests in numerical linear algebra, but also more broadly in things like fluids, data simulation, particle dynamics. So they're kind of people working on problems that perhaps could benefit from this kind of data framing framework in there. Separate to the applied group is the optimization and operational research group. So they have a similar number of staff, and obviously optimization forms a large part of this kind of underpinning of this project. So there are people who kind of have research interests that are aligned in that group too. Additionally, this group is quite, they have quite a lot of industrial focus as well, and partners with industry. So that's kind of something further down the line that we might be interested in exploiting. In addition to the active research that's going on amongst PhD students and staff, and there's also popular MSc programs in well, there's a lot of them, but some of the ones that are most relevant, computational applied mathematics, and lots in operational research that have relationships to statistics, data science, and optimization. So additionally, within Edinburgh, we also have the School of Informatics. So this is a combination of kind of data science, computer science, and things. And there's a lot of things to do with machine learning and deep learning going on in this school. So they kind of focus on generally understanding computation in general, with focuses on everything from kind of like doing algorithms and using computer architectures to developing new neural network approaches and deep learning approaches. So I think, as well as collaboration between the universities, like another nice aspect of a project like this is encouraging interactions between departments within the same universities. So I think the idea is for future half-day workshops, this we're kind of focusing more on optimization. In the future, we're hoping to kind of focus on kind of deep learning, and it would be nice to get collaboration speakers from elsewhere. More broadly within Edinburgh, we also have close links with Heriot-Watt University via the Maxwell Institute. So this is a joint venture between the two universities. And the idea is that it's a hub for mathematical science and training and applications, basically. So we have joint seminar series, and in particular, there's a joint PhD training center on mathematical modeling, analysis, and computation. So in addition to this kind of specific research institute, Edinburgh is the home of the International Centre for Mathematical Sciences. So this is an organization that helps to stimulate and promote mathematical sciences, mainly by hosting and enabling international research visits, workshops, and conferences. So for example, John and I co-organized a workshop at the ICMS last week. And both of these, the Maxwell Institute and ICMS, are located at the Bay Centre in central Edinburgh. So Edinburgh is really a hub for lots of exciting things that are going on in mathematics, but there's always more to be going on. So if you want to come for a research visit, it's a great place to visit. So that's all I wanted to say about Edinburgh. I think it's time to hear about KU Leuven.
May work. Right, so KU Leuven, I also found some helpful graphics from our marketing department. As you can see, our university was founded quite early on, 1425. And it's a quite large general university. So we have study programs in most areas of sciences, humanities, arts, and so on, with about 60,000 students. And even there's a 12,000 international students. Here are many different programs that we have. One of the main things that KU Leuven likes to pride itself with is the fact that it's ranked by Reuters, for example, as one of the most innovative universities in Europe, for sure, and also in the world. So probably a large part of this is due to the engineering department, and this is also the engineering faculty. And this is also where our group, so the numerical analysis and applied mathematics, so mainly identified with this keyword here, NUMA, which is in the Department of Computer Science, which is in the Faculty of Engineering Science. And this is where I'm located at. So our group consists of about 20 professors and about 40 PhD students currently. And there's also WARTS, or Industrial Valorization Manager, and also 3 permanent teaching assistants. One of the programs that we support, so like our main educational program, is this Master of Engineering Science in Mathematical Engineering. So it's like an applied math program, which has 4 focus areas, one of which is this cryptography. Then we also have this data science and AI option. We also focus on industrial process control and also scientific computing and simulation. All right, and so currently, I think the latest statistics are that we have about 100 students in both of the years, so 50 students in each master year. There's 2 master years. And on the left side of the picture, you can see some of our main research domains, so that we at NUMA are investigating. So we have some math for data science and AI, some classic approximation theory, numerical integration. We have some combinatorial optimization at some of the campuses mainly. We have, of course, numerical simulation and multi-scale methods, some control and optimization that you will hear about shortly. In fact, some numerical linear algebra, multilinear algebra, computational science and engineering applications as well. And finally, also some stochastics and uncertainty quantification. So a really broad spectrum of applied and even industrial mathematics. And then finally, so this is some information I pulled from our industrial collaboration web page. So kind of summarizes the strengths of NUMA and the focus areas, let's say, with respect to potential industrial applications. So we have a large in-house experience, as you've seen on the previous slide, many different focus areas. We have also, since we are embedded in the Faculty of Engineering Science, like an engineering mindset, we try to actually solve the problems in industry, not just, of course, aside from the research focus, we also have this more applied focus to help industry. And then finally, of course, an excellent research environment. As you know, Leuven will be a great place to visit for Jemima and Davide. And so here you can see, like in context of our industrial applications, the main focus areas is designing these numerical algorithms, ensuring that they are in fact, traditional numerical analysis, that they are reliable, that they are efficient. And of course, we also like to focus on, as is quite typical in practical applications, large scale problems. Then I think we have a final slide for the outline of the program today. So the introduction should be finished by now, and then we can get started with the first speaker of today that I assume Jemima will introduce. The pointer works.
Excellent. Now I need to ruin everything because there's only one USB port on this screen.
Problem with this. Oh.
Great. Cool, that was good. So our first talk is going to be from John Pearson, who is a reader at the University of Edinburgh. He's going to be telling us about preconditioned iterative methods for multiple saddle point systems arising from PDE-constrained optimization. So thanks, John.
Thank you. Thanks for coming, everyone. Nice to see you either in person or online. So I'm going to talk mainly about the optimal control and numerical linear algebra aspects of this project. In particular, I'm going to talk about some work with Andreas Potschka from Karstal in Germany, where we worked on so-called multiple saddle point systems, which arise from PDE-constrained optimization problems with a view to good preconditioning. Okay, so I'm first going to give a background to PDE-constrained optimization, what roughly it is, iterative solvers for the resulting linear systems, and what a preconditioner is. And then I'm going to derive an optimality system for a particular problem for people who haven't seen problems like this before. I'm going to then use that to motivate why multiple saddle point systems are useful in this context. Saddle point systems themselves are widely used in optimization, but in this setting, an extension to such systems can be very useful. I'll talk about preconditioners for these problems, and then I'm going to largely show some numerical results for problems with box constraints, briefly motivating the active set method that we apply for such problems. Okay, so first of all, a PDE-constrained optimization problem can have many forms, but I'm going to consider one particular structure here, which is that you measure the misfit between one or more state variables and their desired states, which you can think of as some idealized physical objective. And the way that you ensure that y is driven close to y hat here is that you apply some control or energy u to a physical system. So these are measured in some norms. For ease, I'm just considering the L2 norm, for example. And you weight these terms within the cost functional by a half here and beta over 2 here. Beta is some positive regularization parameter. Large beta means you're quite restricted in your physical process in terms of how much control you can apply, because very quickly this term will become large. Small beta means you're freer to apply a lot of energy to the physical system, and you can typically drive y closer to y hat. So there are many applications to such problems. So one example, just a thought experiment really. So suppose you're running a large company and you're managing large quantities of a foodstuff or a chemical, and you want to store these as close as possible to some ideal atmospheric conditions. So some optimal conditions in terms of temperature, humidity, and so on, that enables maximum yield. So this is like to be expensive, so we would like to minimize the cost of doing this. So one could model this as a PDE-constrained optimization problem using a heat equation or something like that as a PDE to model this term here. In this case, you're trying to minimize the misfit between the atmospheric conditions and the ideal atmospheric conditions. So I denote those as y and y hat. U is your energy expended in sort of heating your system to get these idealized conditions. You can alternatively think of this term as a term representing financial cost. And beta is your parameter denoting at what ratio your atmospheric conditions or your financial cost is prioritized, whether you have a lot of money to work on this or not very much. So that's sort of an example of where such a problem may be of interest. There are many other applications. So in fluid flow control, for example, you can think about minimizing turbulence over an airplane wing, something like that. If you're running large-scale chemical reactions, you might have some objective in mind. For example, some reactants emerging at a specific ratio or one reactant dominating. Okay, or in image processing problems, that's another nice example. You have a fairly natural objective because you want your computed image to be a good reflection of your true image. And you have other statistical error terms emerging in the form of a control. And there's a nice link between problems like this and data assimilation problems, for example, from weather forecasting, for instance. Okay, so there are numerous applications of these problems. The two key things are mathematical modeling and numerical solution. From our point of view, they're also very interesting analytical questions. But if we have a nice model for a PDE-constrained optimization problem, and then we apply, for example, a finite element method, which I will do in this talk, although you can select other methods, typically you're faced with a linear system of very high dimension because of the coupled nature of these problems. So a very useful approach for solving such systems is to construct iterative methods where you don't have to store the entire system. Iterative methods, unaccelerated, can be very slow, however. So we want to accelerate this with powerful preconditions. Preconditioners are used to accelerate the convergence of the iterative method. So in that sense, we want the preconditioned system to have some desirable properties. What these are sort of depend on the method we're using it within. But we also want P inverse to be much cheaper to apply to a vector than A inverse. Otherwise, there's no point in applying the precondition. Okay, but if we can find preconditioners with these two properties, there are many advantages to such problems. We can exploit the sparsity and the structure of the matrices to enable us not to have to store the entire system, but in fact only rather small sub-blocks of it. And then we can move to solving large problems rapidly and sometimes in parallel as well. Okay, so I'm really interested in preconditioning for PDE-constrained optimization. And for certain iterative methods, the one I'm really have in mind here is the conjugate gradient method. Okay, convergence is controlled as follows. So for the unpreconditioned conjugate gradient method, convergence is controlled by the ratio of the maximum and the minimum eigenvalues of the system that you're trying to solve. This will be a positive definite system, okay, for us to apply conjugate gradient. Or if you apply a preconditioner, this will be controlled by the ratio of the maximum and the minimum eigenvalues of the preconditioned system. So if you've devised a preconditioner such that you've clustered the eigenvalues much better with your preconditioner, then you're going to get convergence of conjugate gradient much quicker if you use this preconditioner than without, because this condition number is significantly smaller. Of course, like I mentioned, you want to ensure that the preconditioner is cheap to apply. Otherwise, the cost per iteration is prohibitive. Okay, so that's the kind of philosophy. I'm going to talk about multiple saddle point systems, but let's start by saying what a saddle point system is. So this is really a generalized saddle point system in the sense that you have a non-zero term here. So you have here a matrix A, which is symmetric. Usually for the examples I consider here, at least positive semi-definite. You have a matrix B that represents your PDE operator here. You have B transpose, which typically represents the adjoint operator here. And you have a symmetric positive semi-definite matrix C here. And then you have minus C within this block. So two very famous preconditioners for such a problem are as follows. So there's a block diagonal preconditioner where you take the matrix A in the 1-1 block and the Schur complement in the 2-2 block. And a block triangular preconditioner where you take the same two terms here, you can have a plus or a minus here. In fact, they're both reasonably effective strategies, but you also include a B transpose term here. So this is an important quantity. It's called the negative Schur complement of the linear system that you're trying to tackle. So there are some nice spectral properties of these two preconditioned systems here. So in particular, this is a symmetric positive definite matrix as long as A and S are, okay, which means we can apply it within MinRes, okay, in order to solve the entire system, which means convergence can be controlled by the eigenvalues of the preconditioned system. So eigenvalue bounds are very useful. You can see here that you have a nice cluster of negative eigenvalues here and a nice cluster of positive eigenvalues here. So this is very convenient from the point of view of guaranteeing convergence. This is not a positive definite matrix, so you have to use GMRes or ICG or a method for non-symmetric systems. You get a nice eigenvalue result here, but with such non-symmetric solvers, convergence is not controlled just by the eigenvalues. So really, this is the result of particular interest because this also controls the convergence of MinRes. I should point out that if C is 0 and you have a more classical saddle point system on the most fundamental level, this result reduces to there being 3 eigenvalues only, 1, a half of 1 plus square root of 5, a half of 1 minus square root of 5. Okay, the important point is that A and S are in general not practical to apply as preconditioners because forming S may be hugely computationally expensive, maybe more so than solving the system itself. So we need to find good approximations. Okay, so let's examine for a little while how we solve a PDE-constrained optimization problem. So the first thing we need to do is find the optimality conditions which a problem like this needs to satisfy for the solution to hold. So I'm considering a problem of the form that I showed in the very first slide, except the PDE constraint here is very simple. It's just the Poisson equation. And I'm not measuring necessarily this L2 norm over omega, the whole domain, but over omega S, which may be omega, but may be a subdomain of it. So there are 2 ways of finding optimality conditions. You can either find them on the continuous level and then discretize these, Or you can discretize this problem first and then form the discrete Lagrangian, form the optimality conditions on the discrete. We're going to choose the first. As it happens for this problem, the second gives the same equations, although this is not always the case. So the key ingredient is to build the following Lagrangian. So these first two terms here are just the definitions of these squared L2 norms. And then we want to integrate over the entire domain the constraint enforced by a Lagrange multiplier or adjoint variable. Okay, and then in order to find the necessary optimality conditions, we want to find the stationary points of this Lagrangian with respect to y and u and p. Okay, so differentiating with respect to p, colored in red here, so you can see the only term here is this. So if one differentiates this with respect to p, one simply gets back the forward equation, which is the Poisson equation itself. Differentiating with respect to u, so if you think about differentiating the terms in blue, this will give beta times u minus p is equal to 0, integrated is equal to 0, so this must hold almost everywhere in the domain, so this follows. To obtain the adjoint equation, and this is a little bit more work, but one essentially applies the divergence theorem and the product rule in order to rearrange the term p times minus Laplacian y to this form here. These divergence terms here get eliminated by the divergence theorem and the boundary conditions, which means what's left is the derivative with respect to the terms in magenta, which gives us back the adjoint equation. So negative Laplacian of p is equal to y hat minus y, but enforced on whatever omega s is. So if omega s is omega, this would simply be y hat minus y. Okay, so I make this distinction for a reason. So using a finite element method to build these three equations together, this gives the following block system. So I've applied these equations in order. Okay, so K is a famous finite element stiffness matrix. So this is at least symmetric positive semi-definite. It's positive definite if any of the boundary data is Dirichlet. This is a finite element mass matrix. This is certainly symmetric positive definite. And these are both nice matrices to work with, especially the mass matrix, which is well approximated even by its diagonal or a few polynomial iterations using that. MS is a mass matrix acting on the subdomain. Okay, so it's a mass matrix, but only acting on the nodes in whatever omega s is. So if omega s is m, then this just gives a block matrix with m and beta times m. This is our constraint block, and this would be our show complement, at least if ms equals m. Okay, so if ms equals m, then treating this 1-1 block within a saddle point preconditioner is pretty straightforward, because we know how to approximate the inverse of a mass matrix. Well, a diagonal approximation is already a very good start. Chebyshev semi-iteration uses this to give provable and cheap convergence. So this is very nice. What if ms is not equal to m? Well, then this term is singular. Okay. In particular, if omega s is a very small subset of omega, which is very possible, this would be highly singular. So I would not recommend the saddle point approach at all, because it's difficult to well approximate the inverse of a matrix, which doesn't have an inverse. Okay, so there's a better way to go in such a set. Okay, so I should say in this case, there are many good alternatives for the show complement if omega s equals m. You can drop this term here, the second term, or you can use what's called a matching strategy to capture both terms of the show complement. I'm really going to focus on an alternative. So let me take a step back and tell you what a multiple saddle point system is. So in its most general form, a block tridiagonal multiple saddle point system is of this form here. So on the diagonal entries, you have A0, A1, A2, AK minus 1, AK. All of these are symmetric positive semi-definite with A positive definite. And then you have pluses and minus signs alternating there. And then you have, if you like, constraint blocks beta 1 through to beta k. And this is symmetric because you have the transpose of these terms on the super diagonal. So these are all matrices. So this is block tridiagonal. And you can imagine if k is even reasonably large, plugging this into a direct solver would create a lot of work for the computer. So it'd be nice to have a preconditioner for such a matrix. I'll make the point here that if you take the index k here to be equal to 1, you return straight away to the saddle point framework that I've just described. Okay, so a popular choice of preconditioner here is the block diagonal matrix given as follows. And this is again an ideal preconditioner because these need to be approximated in order to get an effective computational implementation. But I'll come back to this. Okay, so S1 is defined as for the general or classical saddle point system as follows, and S2, S3, and so on are defined recursively in terms of the previous Schur complements. So note that these structures of these Schur complements seem to be getting worse and worse, or more and more difficult, because every time you add complexity to one Schur complement, it's then fed into the next one. Okay, so block diagonal precondition actually does a very good job. We propose another alternative which performs very well. So this is a very nice result here. And this really illustrates what goes on. It considers a setting where A1, A2, all the way up to AK, all 0. Okay, so it's given like quite a heavy assumption, but these systems are very difficult to analyze, and this is very illustrative what we get out of this. So we're assuming that the Schur complements are symmetric positive definite, which is fair enough, because if they're not, then this preconditioner wouldn't even be invertible. We make this further assumption for this result. Then the eigenvalues of the preconditioned system with this block diagonal preconditioner are given as follows. Okay, so if k gets larger, then there's a larger and larger range of j, which means there's a larger and larger range of I, which means there's a combination of I and j, which gets this term here closer and closer to pi over 2 as k increases. Okay, so what this means is that the larger is the value of k, the closer some of the eigenvalues will be to 0, which means your preconditioned matrix becomes increasingly ill-conditioned, which means you can't obtain as robust convergence for larger values of k. This is fair enough because it's a tougher problem, so you can't really expect as good a convergence for it. However, this is a result which motivates a strategy which maybe doesn't have this feature. And what we, I should say actually, so what's known in practice in the general case, so this makes the assumption that these matrices are 0. Analyzing this, if they're not 0, is very difficult, actually, and this in fact only known, as far as I know, for very few values of k. So k is 1 goes back to the saddle point system. I presented that already. So this is quite a famous result. So two groups, one of which was Andreas and myself, and one of which was Suzanne Bradby and Ken Greif from UBC, had analyzed this case and found that this is now the eigenvalue range for k is 2. So you can see, as expected, the eigenvalue range is expanding out, and this in particular becomes much closer to 0. K is 3 we analyzed as well, and this becomes the eigenvalue range here. And you can see now this becomes much closer to 0. So you can see there seem to be some patterns in the eigenvalue bands for, or at least very small values of k. What we can say is that this backs up what we expect, which is that you get more eigenvalues close to 0 in particular as k increases, at least for small k. These are some plots which I generated just with some randomly generated examples. So in more detail, all I did here was I randomly picked sizes of the blocks. I created AI and BI randomly. Then I symmetrized A and added an identity matrix on, which ensured that it was either positive definite or positive semi-definite. I ran it for 100 different examples and then plot all the eigenvalues. Okay, and these are how they behave with respect to the bounds. Okay, so an alternative proposal for a preconditioner, which we've made, is the following one here. So instead of PD as a preconditioner, we're proposing the following matrix here, where PL is, if you like, an analog to the lower triangular preconditioner for a classical saddle point system. So again, you have alternating plus and minus signs on the block diagonal entries. You have all the constraint blocks appearing here. So this forms PL, and you can see the main computational work here to apply the inverse of PL is essentially the same as that as PD, because you're approximating the inverse of these blocks or approximations of them. PD inverse PL transpose conveniently simplifies to this matrix here, which means the main work is approximating the inverse of A0, S1, all the way up to SK minus 1. So there's more work here to do than with a block diagonal preconditioner, because you're approximating the inverse of A0 all the way up to SK minus 1 twice rather than once. However, you're only approximating the inverse of SK one time. That's the same as the block diagonal preconditioner, and that's a nice feature of this as well. Because like we say, the last Schur complement is very often the most difficult. So if you can experience a drastic reduction of iteration numbers, there may be some gain in applying this preconditioner with the same Schur complement approximations as you would apply within the block diagonal preconditioner. So these are just a couple of results which we proved about this new preconditioner. So for any k, the preconditioned matrix PK inverse AK, okay, if and probably is a reasonably big if you apply each of these terms inverse exactly, which you wouldn't do, okay, but if you apply it exactly, the preconditioned system has only 2 distinct eigenvalues, and those are equal to 1 and minus 1. Okay, and that's for any k. We also showed that if you approximate only the last Schur complement with a symmetric positive definite approximation SK hat, then the eigenvalues of the preconditioned system are equal to either 1, minus 1, or within the range of this matrix here. So essentially controlled by how effective your approximation of the final Schur complement is. In practice, you would try to approximate everything, right? But this is an illustrative result, in particular in the setting that the last Schur complement is the most difficult to approximate, okay, which we can reasonably expect it will be for a number of problems. So this is nice because these bands don't depend on k. So I'll give you an idea here of how the eigenvalues behave when we do take approximations. Okay, so this is these are the eigenvalues of the preconditioned system for approximations of the block diagonal and new preconditioners for a range of different values of k. So again, I've randomly chosen the problem sizes here. I've constructed the matrices in the same way, and then what I've effectively done here is I've taken the exact terms of A0 and all the show complements, and then multiplied them by randomly chosen constants. Okay, and just seen how this behaves when we take approximations. So the eigenvalues in blue are the eigenvalues of the preconditioned system with the block diagonal preconditioner. The red eigenvalues are those of the preconditioned system with the new preconditioner. And we can see in particular that the eigenvalues in red are much further away from the origin than the eigenvalues in blue. This suggests we're going to get faster convergence, or at least in fewer iterations. You can see that in practice, when you add an approximation in here, the eigenvalues of both red and blue do approach the origin as k increases, but the red one's slower. Okay, so this seems that it may be promising to use such an approach. So let's go back to PDE-constrained optimization and figure out whether this is worth doing for at least this problem here. Okay, so I'm going to consider a form of PDE-constrained optimization problem which I've already shown you. I called this omega s before, so a subdomain of omega. Here, omega s is going to be the boundary of omega. So what this problem means is that I want to observe how closely y it resembles y hat only on the boundary of the domain. That's what I'm interested in. Okay, and I take the Poisson equation and add this term in here to just really to ensure the invertibility of this term here. Don't need this term really, you can get similar results otherwise. Okay, and I take Neumann boundary conditions. So for the reasons I explained earlier, this wouldn't be worth solving using a classical saddle point approach because you get a highly singular 1-1 block. But rearranging this allows us to get this this block triangular multiple saddle point system here, okay, for which A0 and all the show complements are well defined. So A0 is a mass matrix multiplied by beta. S1 is M times beta M all inverse M, so 1 over beta times M, also a mass matrix. We know how to deal with this with just a few iterations of Chebyshev semi-iteration. We use 5 for this example. S2 is this matrix here. And for the sake of our experiments, what we do is we choose to drop this second term here. So in order to approximate K2, within our preconditioner, we're going to apply a multigrid cycle to approximate the inverse of this. This, when you apply its inverse, will just turn into a matrix times vector multiplication and a multigrid cycle for this. So we use 2 multigrid cycles specifically for each of these matrices. So these are the results to obtain a tolerance of, I think it was 10 to the minus 8 using the Page and Saunders min-res routine, which considers a stopping criterion based on the backward error. We test the same for each example, the same approximations for A0 and the show complements using the block diagonal preconditioner and the new preconditioner. Okay, so here is a range of problem sizes. So they go up to a problem size of about 3 million and a range of regularization parameters beta. So numbers in blue are the min-res counts for the block diagonal preconditioner and the ones in red for the new preconditioner. We can see that there's a significant gain for this problem between the numbers in blue and the numbers in red. And I think the CPU times are all lower for the new preconditioner as well. Okay, so although the new preconditioner is more, it has more computational work per iteration, the reduction in iteration numbers is sufficient that overall we get a gain in CPU time. Okay, so this was with 5 Chebyshev semi-iterations here for approximating a mass matrix and 2 multigrid cycles here. This is a nice example because we can test both preconditioners at the limit. So in particular, we can control here how well we approximate M inverse. And this gives a good indication of when I wouldn't apply the new preconditioner. Okay, so if I approximate M inverse with varying numbers of Chebyshev semi-iterations, which are denoted here, okay, I'm going to fix beta for this example, get similar observations for all beta, in fact, vary H. Okay, and I just report the iteration numbers here. So remember, we have to approximate A inverse and S1 twice, which means that if we haven't done a very good job approximating them, then we sort of get hit by this twice within the preconditioner. This wouldn't happen within the block diagonal preconditioner because they're only applied once. So if I take a deliberately bad approximation of these two matrices here, so if I just take one Chebyshev iteration, then the iteration numbers here are not much worse than the iteration numbers here. And in fact, because of the expense of applying the new preconditioner, you get slightly higher CPU time applying this one than this one. So this highlights an important point, which is that you really want to be doing quite well with your approximations of the Schur complements in order to get the maximum benefit out of this new preconditioner. If you take two iterations, so if you take a second one, which is very cheap, then already you're gaining quite a lot in the iteration numbers and the CPU time. Okay, but this is just a note here that you really want to put some effort into approximating these two terms, which for this problem is worth doing anyway, because these two terms are very cheap to approximate compared to the final Schur complement. Okay, so I'm going to talk very briefly now about some application of this to difficult problems with box constraints. So what I'm going to consider here is a similar type of problem, but I'm now imposing box constraints on the state. So y plus is a given function, a given continuous function on omega, and I want to satisfy these box constraints. So state constraints are very difficult in PDE-constrained optimization, certainly on an analytical level, because the Lagrange multipliers are only measures in general and thus exhibit only low regularity, which can numerically also impact your efficiency. Okay, so I'm going to not talk very much about the details of this approach, but I refer you to the paper for the details. What we're going to use is a so-called sequential homotopy method. The first step here is to introduce a lifting variable, which is called y tilde, which is in the largest space, L2, as opposed to H1. Okay, so all we say here is that I'm going to set y equal to y tilde in omega, and I'm going to instead enforce the box constraints on that. Okay, the nice feature of this is that the Lagrange multipliers now have higher regularity. So there are two now, one enforcing the PD and one enforcing this, but this now has regularity H1 and this L2. Right, so which leads to beneficial properties. Okay, and broadly speaking, what we do is we solve a system of subproblems which involves augmenting the Lagrangian with an augmentation term involving a parameter rho. The augmentation term essentially adds on to the objective function the norm of the constraints as well. So if you're solving exactly, is adding 0, but it adds on this term multiplied by an augmentation parameter rho. And also we're adding on a regularization involving a parameter lambda. So you can think, I would think just for the sake of this metric system, that lambda and rho are small parameters. At least that we want to solve this system for small parameters. Okay, and this can be phrased as an active set method. So what this means is that at each iteration, you consider the nodes at which y tilde are equal to y plus, and they're then members of the active set, and where y tilde is strictly less than y plus, they're then classed as inactive indices, which means that we include them in the next linear system. So the first index here, I, corresponds to the subset of rows, and the second to the subset of columns. So MII in particular is the mass matrix defined over the inactive nodes. MI colon is analogously the mass matrix where we're just looking at the rows in terms of the inactive nodes. That's this nice feature that it can be regarded as a backward Euler step of a projected gradient anti-gradient flow. Okay, but I'm not discussing this. This is the motivation of this parameter. You can think of these as small parameters. Okay, so you can see here that this might be quite a tricky matrix system to solve, because if you have small parameters here, you have matrices working on many scales. You have some very large, some terms which could be large depending on the level of the grid, but also multiplied by a small constant. This can be quite difficult in terms of even devising approximations for the Schur complements, right? So in the notation of multiple saddle point systems, A0, A1, A2, A3, A4 are just the block diagonal entries, either taking a plus or a minus sign before them. These are the constraint blocks. Okay, and the Schur complements are defined like this. This is just plugging in the previous Schur complements in. Okay, so I just want to talk briefly about how we approximate each of these Schur complements before showing you some results. So A0 is easy because it's a positive factor multiplied by a mass matrix. S1 is relatively easy because it's simply something times a stiffness matrix plus something times a mass matrix, so we can apply a multi-grid method to it. S2 starts becoming a little difficult because you obviously don't want to form this inverse, so you need to come up with some ways of dropping some terms. So we first drop the terms multiplied by lambda. We're interested in the case, particularly where lambda is small. So we first approximate S2 by this. This is actually a very good approximation. Okay, you can consider that the eigenvalues of S2 tilde inverse times S2 are very clustered. Okay, and then we approximate S2 tilde using the matching strategy that I mentioned earlier, which means that instead of ever having to form this matrix M, we can apply this within using a multi-grid cycle, and this using a multi-grid cycle, and this is a vector matrix vector multiplication. And then we scale it actually so that the eigenvalues of this preconditioned matrix are, if you like, geometrically symmetrized about 1. Okay, so for S3, we neglect the first term because it's very small. In general, it's lambda multiplied by quite a small matrix. So then we feed in our approximation for S2 to write S3 hat inverse is this, which means if we want to apply this on a computer, this involves 3 approximations of the inverse of a mass matrix acting on a vector, which is nice, and some matrix vector multiplications. S4, we regard these matrices here as projecting onto the inactive set, and then we take this approximation here using the same matching strategy as for S2. But these are the choices we've made. There could possibly be better choices to be made. The point is we make these choices for both the block diagonal preconditioner and the new preconditioner. So this is our problem data. We solve it on a disk. And this is what we use. We use, again, 5 Chebyshev semi-iterations to approximate the inverse of a mass matrix. We use 4 V cycles to approximate terms that look like this. Consider a range of small values of lambda and beta, and a range of values of H. And what we can see here is, again, the new preconditioner seems to reduce the iteration count substantially. We don't have complete mesh robustness, especially for the large values of beta. It's a very tough system. And we can see that if we compare the iteration numbers, we get better performance using this modified preconditioner. And the CPU times also reflect this. Okay, as I'm running out of time, I'm just going to show you some numerical results for a problem with control constraints. This is a highly nonlinear problem now that I'm considering, because I'm going to consider the nonlinear part of this PDE to be 4 orders of magnitude larger than the linear part. So this is a very tough problem. Low regularization parameter, which also makes life difficult. So a solution of nonlinear PDE constrained optimization adds many extra difficulties, which I could well talk about. But I'm just going to show you some numerical results here. So I'm going to bound U by minus 50 and 50. Okay, and what I'm going to illustrate the result as here are the outer active set methods iteration K, and on the y-axis the number of inner Krylov iterations at each iteration. Okay, we cap the iterations at 100, so if it hasn't converged to our tolerance in 100 iterations, we move on to the next. Okay, but these are all indicated here. Okay, and what we can see here is that in almost all iterations, both the block diagonal and in fact the block triangular preconditioner. We haven't tested actually the new preconditioner on this example because of we used the PETSI implementations for these preconditioners for a block system, and we haven't implemented the new one yet. But what we see is a fairly reliable set of Krylov iteration numbers. We get a few occasions where, especially for the very fine meshes, we don't get convergence in 100, but we get good enough convergence that in a few more iterations, the solution gets back on the right track and we get convergence. The block triangular preconditioner, although the eigenvalue theory doesn't apply, is more reliable, as you can see with the number of iterations, and that is why we achieve convergence for the same problem in fewer outer iterations. And just few more illustrations. So this is the wall clock time when taking a direct solution. Okay, and these are the wall clock times when taking block diagonal and block triangular preconditions. This is only for a 2D problem. So you're saving quite a lot by taking the preconditioner as opposed to the direct solver. Usually you see this feature substantially more for 3D problems. So this is nice that we're already gaining some CPU time here. We did some weak scaling experiments as well. So it seems to have reasonably good parallelizability, where there's a bit of drop off here between running 16 and 64 processors. And we find this is usually due to the multi-grid routine. So this could be improved here. But in the last case, we're solving a problem of 19 million or so in order of 10 seconds. So we're pretty happy with those results as well. Quite a tough nonlinear problem. Okay, so that's all I wanted to say really. So PDE constrained optimization has numerous applications. That's probably the first thing worth saying. So numerical solutions are very important. A new observation on the preconditioning of multiple saddle point systems, we think can give some insights into the solution of such problems for various numbers of blocks. And we saw some significant gains there in a number of numerical tests. There are some theoretical guarantees provided, at least in some idealized settings. And we've also shown at the end an inexact active set method for large-scale PDE constrained optimization problems, which allow us to tackle some tough problems with additional state and control constraints. That's what I wanted to say, so thank you very much.
I'll start by asking if we have any questions in the room for John.
I have actually a couple of questions. So like in the results that you showed about the problem without the box constraints, like the number of iterations when you were using beta, like this, something like this, like increase, and then for the smaller the smallest beta, you had a drop in this
This one here, or?
Yeah, exactly. So you have like, for instance, the first row 17, 21, 20. But as you mentioned, like having a small beta makes the problem harder. So do you have any insights about this phenomenon?
I think this might have, there are a couple of things here. It's partially probably to do with the tolerance which the MinRes is set based on the backward error analysis. So the MinRes code doesn't use a standard sort of, we stop MinRes when we get the following reduction on the residual.
So it's like the denominator in your backward arrow that gets.
So because of this term here, the S1 block is more dominant, I think, in the sense of the preconditioner, which is why the quality of the approximation of S2 seems to be less important by way of convergence. So that's why I think that is what's happening. It's because this term dominates the character of the system a little more.
Okay. The second question is like, why multiple solder point systems and not symmetric block triangular? Like, these techniques would work for any symmetric block triangular system or not?
These methods.
Yeah. Preconditioning.
We're preconditioning block tridiagonal systems using matrices of this form here. I mean, I would say yes, with the obvious caveat that you'd need to be able to approximate these Schur complements well. I mean, I think that's a condition you need more or less for any solver to work well. But providing you have these good approximations, and especially if you can approximate these early blocks well, then I think it has wide utility. Yeah.
Because also, like, the theorem you showed was based more on the tridiagonal structure, block tridiagonal structure of the system, right?
Yeah, exactly. Yeah. I mean, it's so yeah, we focus more on the show the system again, where these terms are zeros. It's quite likely that we could extend this to problems where either these subdiagonal terms appear in different blocks or where there are additional terms coming in here. We haven't tried this mainly because we're not aware of so many systems with clear applications in that direction yet, for which we could have come up with a good approximation of the Schur complement. So that's why we focus on this.
Thank you.
I don't believe we have any questions from Zoom. So in the interest of time, let's say thanks for John again. A brief break / technical interlude and resume in 8 minutes for our first online.
Right.
Oh, nice.